We've built the machine. 5 variables, 6 parameters, feedback loops connecting everything to everything. Now comes the question every engineer asks: where does this system settle? What are the stable states? In system dynamics, we call these equilibrium points. And finding them tells us something profound, not just where a political economy can rest, but which resting points are stable, which are fragile, and which are impossible to maintain. This is Module 4, Model Analysis. Let's find the equilibria. An equilibrium is a state where nothing changes. All the derivatives equal 0, and the system has found a balance point. Mathematically, we're looking for values of w, n, l, e, and p such that dww dt equals 0, dn dt equals 0, dl dt equals 0, de dt equals 0, dp dt equals 0. All 5 rates of change simultaneously equal 0. But here's the crucial insight. An equilibrium existing doesn't mean the system will reach it, and reaching an equilibrium doesn't mean the system will stay there. We need to distinguish 3 types. A stable equilibrium is like a ball at the bottom of a bowl. Push it slightly, and it rolls back. The system returns to equilibrium after small disturbances. An unstable equilibrium is like a ball balanced on top of a hill. The slightest push sends it rolling away, never to return. The equilibrium exists mathematically, but the system can't maintain it. A saddle point is stable in some directions and unstable in others. Like a mountain pass. The ball can rest there, but only if you approach from exactly the right angle. Political economies exhibit all 3 types. Understanding which equilibria are stable tells us which political arrangements can actually persist. How do we find equilibria in Saylor's model? We set each differential equation to 0 and solve the system simultaneously. This is easier said than done with 5 nonlinear equations, but the structure helps us. Start with the economic sector. At equilibrium, production capacity P is constant. That means investment equals depreciation. Given the parameters, this pins down a relationship between P and other variables. Move to the executive sector. E is constant when power generation equals power expenditure plus decay. This creates another constraint. The legislative sector at equilibrium means pressure for change equals resistance to change. L settles where political forces balance. Social norms N are constant when norm building equals norm erosion. This depends heavily on conflict levels, and conflict itself, though derived from C, which comes from W, reaches equilibrium when wealth distribution stabilizes. Each equation constrains the solution. Where all constraints intersect, we find equilibrium points. The mathematics can get complex, but the intuition is straightforward. Equilibrium occurs when every force in the system finds its counterforce. Here's where it gets interesting. Saylor's model doesn't have just one equilibrium. It has multiple equilibria, and they correspond to recognizable political arrangements. Consider 2 extreme cases. First, high W, low N, high E. Wealth is concentrated. Norms are weak. Executive power is strong. This is the autocratic equilibrium. A strong man maintains order through force. Inequality is high, but conflict is suppressed. The system can be stable if E is sufficient to contain the pressure. Second, low W, high N, moderate L. Wealth is distributed. Norms are strong. Legislation responds to democratic pressure. This is the democratic equilibrium. Conflict is managed through legitimate political channels. No single actor dominates. Between these extremes lie other possibilities. Oligarchic equilibria, where a small elite captures both wealth and political power. Unstable transition zones where no arrangement can persist. And mixed regimes that combine elements. The key insight: different parameter values support different equilibria. A society's equilibrium possibilities depend on its underlying characteristics, the alpha, beta, gamma, delta, epsilon, and tau that define it. Change the parameters, and you change which equilibria exist. Finding an equilibrium is just the first step. We need to know if it's stable. The standard technique is linearization. Near an equilibrium point, we approximate the nonlinear system with a linear one. The behavior of this linear approximation tells us about local stability. We compute the Jacobian matrix, the matrix of all partial derivatives, evaluated at the equilibrium. The eigenvalues of this matrix determine stability. If all eigenvalues have negative real parts, the equilibrium is stable. Perturbations decay over time. If any eigenvalue has a positive real part, the equilibrium is unstable. Small disturbances grow exponentially. If eigenvalues are purely imaginary, we get oscillations. The system cycles around the equilibrium without settling. For Saylor's model, the Jacobian is 5 by 5. Computing eigenvalues requires numerical methods for realistic parameter values. But the structure reveals important patterns. The feedback loops we identified, reinforcing loops, drive eigenvalues positive, creating instability. Balancing loops drive eigenvalues negative, creating stability. The balance between these determines whether an equilibrium can persist. Even stable equilibria have limits. The basin of attraction defines how far you can push the system before it escapes to a different equilibrium. Imagine the state space as a landscape with multiple valleys. Each valley is a stable equilibrium. The ridges between valleys are the boundaries of basins of attraction. If the system starts inside a basin, it flows toward that equilibrium. But push it over a ridge, and it flows toward a different one. This matters enormously for policy. A society near the center of a democratic basin can absorb significant shocks. Recessions, political scandals, even crises. It returns to democratic equilibrium. But a society near the edge of that basin is fragile. The same shock that a robust democracy absorbs might push a fragile democracy into autocratic collapse. Saylor's model lets us ask, how large are the basins? What determines their boundaries? Which policies expand the democratic basin versus shrink it? These aren't just academic questions. They're about the resilience of political systems. Sometimes changing a parameter doesn't just move an equilibrium. It eliminates equilibria entirely or creates new ones. These critical transitions are called bifurcations. Consider what happens as wealth concentration W increases slowly. At low W, a stable democratic equilibrium exists. Conflict is manageable. Norms hold. The system maintains itself. As W rises, the equilibrium shifts. L moves toward more redistributive policy. N faces more erosion pressure. The system adjusts, but persists. But at some critical W value, something qualitative happens. The democratic equilibrium becomes unstable, or it simply vanishes. The only remaining stable state might be autocratic. This is a bifurcation point. Before it, democracy is possible. After it, democracy is mathematically impossible given the system's parameters. Bifurcations explain why gradual changes can produce sudden collapses. The straw that breaks the camel's back isn't special. It's simply the straw that crosses a bifurcation threshold. In political terms, rising inequality doesn't linearly erode democracy. It does nothing visible until suddenly it destroys the possibility of democratic equilibrium entirely. What does equilibrium analysis tell us about real political economies? First, multiple stable states exist. History isn't deterministic. Societies with similar fundamentals can end up in very different equilibria depending on initial conditions and historical accidents. Second, stability isn't guaranteed. An equilibrium existing doesn't mean it will persist. External shocks, parameter drift, or simple bad luck can push systems out of stable basins. Third, transitions between equilibria can be sudden. Bifurcations mean gradual pressure can produce discontinuous change. Revolutions, collapses, and rapid democratizations become mathematically explicable. Fourth, resilience depends on basin size. Some equilibria are more robust than others. Policy should aim to expand the basin of desirable equilibria, not just reach them. Fifth, early warning signs exist. As systems approach bifurcation points, certain indicators change: longer recovery times from small shocks, increased variance, critical slowing down. These are the canaries in the coal mine. This is the power of Saylor's approach, turning qualitative political intuitions into quantitative, testable predictions. We've found the equilibria. We've analyzed their stability. We've mapped the basins and identified the bifurcations. Next episode, we'll put the model in motion. What happens when we simulate Saylor's system? How do different societies evolve over time? Can we reproduce historical patterns? Simulation lets us watch political economies unfold, fast-forwarding through decades in seconds, running the same society with different parameters, testing interventions before implementing them. Your challenge? Think about a political transition you know, a democratization, a collapse into autocracy, a revolution. Frame it as movement between equilibria. What pushed the system out of one basin and into another? Was it a parameter change? A shock? Gradual drift toward a bifurcation? This is how systems thinking illuminates history. Next time, simulation and scenarios.